Flare and glare are common nighttime artifacts that degrade image quality and visibility. Glare results from diffraction and scattering at the aperture or surface imperfections, while flare is caused by Fresnel reflections within lens elements. Nighttime flare and glare obscure key scene details, reducing contrast and detection accuracy, and challenging computer vision tasks such as autonomous driving and object recognition. Their complex shapes and diverse patterns make removal extremely difficult. Effective removal is essential to improve the robustness of vision systems under real-world lighting conditions. Existing synthetic datasets lack physical realism and diversity. They fail to reproduce the complex diffraction and reflection patterns found in real cameras, limiting model generalization and leaving residual artifacts after restoration. Previous removal methods struggle with severe flare and glare. Most focus on small bright regions and fail to recover fine textures or background details. Our goal is to overcome these limitations with a physically accurate dataset and an effective restoration network. We introduce PBFG, a physically based flare and glare dataset. It includes 120 flare and 168 glare pattern types, rendered using realistic optical parameters such as f-number, aperture shape, and coding effects. Our dataset enables physically faithful training for deep learning models. Our dataset is generated through a physically based computational rendering scheme. A compound pattern is synthesized by combining two key components, flare and glare. By integrating these effects, PBFG produces realistic, physically accurate compound artifacts seen in real cameras. The glare pattern is composed of starburst, glow, shimmer, and streaks. For starburst, glow, and shimmer, each is controlled by optical parameters such as polygon size, f-number, and dot or line density. Random dots and lines simulate lens dust and scratches to simulate glow and shimmer, while spectral integration produces smooth color transitions caused by chromatic aberration. This physically based pipeline enables flexible and diverse glare synthesis that matches real optical behavior. Streaks often appear as asymmetric light rays with varied lengths and blurred edges. To capture these complex patterns, we introduce an advanced streak synthesis method based on the aperture geometry. By iteratively generating curved edges and combining multiple streak segments, our method produces controllable and diverse streak patterns that closely match real diffraction effects. Flare patterns are simulated through ray tracing in 15 optical system configurations. Each setup models realistic interreflections, aberrations, and codings. 8 aperture f-numbers are included, ranging from f/2 to f/22, producing physically accurate flare patterns for diverse lighting conditions. Each stage integrates flare and glare removal transformer blocks that combine spatial and frequency domain learning. This design enhances both local detail and global context understanding. The SFEM replaces the standard feed-forward network with a dual-branch design. The spatial reconstruction unit refines local details by separating informative features, while the frequency-enhanced unit captures global frequency information using real FFT. Their spatial and frequency fusion improves effective artifact removal. When strong glare dominates a scene, the output color distribution may deviate from the ground truth. The HM module aligns the output and reference images using channel-wise histogram matching, ensuring realistic color consistency and natural visual tone. To test generalization, we trained identical models on different datasets. Models trained on PBFG outperform those trained on Flare 7K and Flare 7K++, achieving cleaner results on real-world images and confirming PBFG's physical accuracy and practical effectiveness. Compared to existing methods, our network removes both flare and glare even in complex cases with multiple light sources and long streaks. Competing approaches leave residual glare or streaks, while FGRNet successfully restores hidden background details. In conclusion, PBFG provides the first physically based dataset for flare and glare removal, and FGRNet achieves state-of-the-art performance. Together, they significantly enhance realism, accuracy, and robustness in nighttime image restoration.